In this video, I want to make a follow-up to the video released earlier in the week by Matt Rocklin, which talks through accelerating Python code using a few different techniques, going from optimizing on one CPU, scaling out over multiple CPU cores, and then moving to a GPU to get much larger parallelism. It's an awesome video. I highly recommend you go and check it out. One thing that I was thinking whilst watching that video is when you get through to the GPU section, and get the kind of blistering speeds that those kind of GPUs can give you. I was thinking the machine that was running on is a really nice high-end multi-GPU server. It's the kind of thing that if you had a real solid use case for GPUs, you'd aspire to go out and buy and try and make as best use of it as possible. But if you're kind of new to GPU computing, you're not sure whether you can get value in your workflow and you want to kind of explore and experiment, you're more likely to have a kind of consumer end GPU. Maybe it's something in a machine you already have, or you would look at going out and purchasing maybe a lower end card. So I wanted to make kind of a follow-up video that shows the similar kind of performance increases, but on a more commodity GPU. So in this demo, I'm going to be using my own laptop. This is a laptop that I bought on Black Friday last year. I think I paid about $800 for it, so slightly less than the price that's there at the moment. This is an MSI gaming laptop. It's one of the cheapest gaming laptops that seems to be around. I chose it just because it had a nice balance of a few different things. It's got a decent CPU, paired with a relatively bog standard GPU, a GTX 1050. I don't do a huge amount of gaming, and when I do, I normally end up just buying whichever game that came out 5 years ago is on sale on Steam. So I don't need anything particularly demanding. But the first thing that I ended up playing when I got this laptop was Firewatch, and it looked absolutely amazing on this machine. I also, one of the huge things that made me lean towards this machine was the weight of it. So it's about 1.8 kilos, which is roughly the same weight as a MacBook Pro of the same size. And it's about half the weight of an equivalent Alienware or Dell gaming laptop. So I wanted something that would allow me to play some games, have a discrete graphics card, but was relatively light and portable. So I ended up going for this machine. I've been very happy with it. And then another thing I'm able to do is do work on Python on this machine. And so I'm going to walk through basically the same example just to show the performance differences between the CPU and the GPU of this machine. So we have our kind of original function here. This is our Python function where we're going to iterate over a random array, and we're going to smooth the array based on the values of all the cells around it. Now, if we just kind of comment out the number code, we can run through this and have a look at how long it takes to do one operation. So I'm just going to run this in pure Python. We're going to gather our data, we're going to call smooth, we're going to do an FFT on it, and then we're going to mock saving it out as well. So that took about 3 seconds to do that in pure Python. If we turn number back on, we're going to JIT compile this code the first time that we run it. So this will optimize the code, compile it using LLVM, and then execute. It took about half a second. We now don't need to compile it again because that should be cached. So if we run it a second time, that function goes a lot faster. So we can turn up the number of times we're going to iterate over this. So let's go for 50. And this is going to take roughly the same amount of time that it took to do one operation in Python. We can now do 50 operations using the number JIT decorated version of this. Now this code is going to be pretty familiar to anybody that's used to writing C or Fortran and doing this kind of numeric computation. Now let's have a look at seeing how this kind of code will perform on the GPU in this laptop. So we have roughly the same code here. This is the same code from the other example video. The way that this works from a CUDA point of view is a very slightly different function. And the main difference between CPU and GPU computing is that the GPU is going to execute many threads in one go. And the way that CUDA works is you have a function that you're going to execute lots of times concurrently, and the GPU is going to handle managing that. So there's a few differences in the way that you have to write your code to deal with that. One is that we don't need our for loops because the GPU is going to handle parallelizing calling our function. Instead of iterating over our array, we can simply ask the GPU, which thread am I within a two-dimensional grid of threads. So the GPU will execute lots of threads. They'll be laid out in a grid, and you can say, where am I in this grid? And in that case, I'm just going to operate on the section of the array that corresponds to my index within the CuPy array. So we're using CuPy here, which is the GPU version of NumPy. The other thing that we can't do within our CUDA function is return anything, because we're operating on small sections of the array. We don't have to want to deal with piecing them back together and moving things around. So what we do instead of passing our array in is we're actually going to pass in our array and then another empty array of the same shape and size. And then instead of returning our output array, we're just going to update the values of the output array in place here. Other than that, it's pretty much the same. We've changed our decorator, so it's number.cuda.jit instead of number.jit. But then when we call it, this code down here is exactly the same. We're going to gather our data from the detector. We're going to smooth it using our new GPU smoothing function. We're going to FFT again, and then we're going to mock saving it out. Another nice thing here is that NumPy recently became aware of other types of array. So we have we're importing CuPy and creating a CuPy array here, but we can still use NumPy to call our FFT on that array. NumPy will just look at it and go, oh, that's not a NumPy array, that's a CuPy array. I need to dispatch off to the CuPy version of FFT, and that will come back. But it means the only code that we've had to change in terms of NumPy is just where we're constructing our array up here. So if I create our array function, and then I'm going to run this 50 times again, instead of this taking 3 seconds, this is going to take just a couple of seconds. For the compilation, it took a little bit longer, but now when we're running it, we're taking 155 milliseconds. So it's much, much faster. So we can look at bumping this number up again. Maybe we go up to 100. It's taking a quarter of a second. We could go up to 1,000. It's taking a little bit longer, 1.6 seconds. So if we go for maybe 3,000 times, we're back to roughly around the 3 second mark. Where are we? Is it going to give us 5.3 seconds? Okay, maybe I'm being slightly optimistic. If I run this 2,000 times, on the GPU in my laptop, 3.5 seconds. So being able to rewrite this code very slightly using CUDA and run it on the GPU in this machine, I can do it 2,000 times in the amount of time that it took to run once in pure Python. So that's what I wanted to cover is you can do this kind of work on more commodity GPU hardware. So you could go out and pick up a laptop like this and use it for local development and exploration, and then when you start seeing the value and getting good results out of being able to accelerate your code in this way, that's the point that you can then go out and look at maybe getting higher end cards and servers and things. So thank you very much for your time.